Dr. Mohamed Ahsan Mohamed Mafez was a PhD student at Coventry University until recently, but he defended his PhD and now is a doctor. And he's going to talk about fault-tolerant control for multirotor UAVs. Okay, you can go ahead.
Okay, just a quick check. Can everyone see my slides and am I very clear to everyone?
Yes.
Okay, perfect. My name is Ahsan and I'm from the Research Center for Computational Science and Mathematical Modeling at Coventry University. Thank you so much, Amir, for this opportunity to present at this conference. I'll be talking about fault-tolerant control for multi-rotor UAVs. I'm sure many of us here would have heard about drones, UAVs, and these technologies. They are used pretty much in various different industries, and now we see this expanding exponentially. So today's topic would be how fault-tolerant control is useful and can help stabilize drones into like a more safer mode of transport. Now, the first question that might come up in mind is what really makes UAV control a problem? I would start with model uncertainties. There are many drones out there, but all these drones, when they are designed, they are designed based on a mathematical model, and this mathematical model is not always accurate. There are so many uncertainties. For example, system degradation, there are unmodeled dynamics, payload variations, and so many. And according to the literature, it is evident that there is no perfect mathematical model to capture the entire dynamics of a quadcopter. Then, when you design a drone and you go out to fly, there are external perturbation. These can be wind, turbulence, and many other factors. For instance, in the UK, it is very windy, and during windy times, the drones are a bit uncertain because they might drift slightly away from their reference point. So taking into these external perturbation into account when designing a control for a drone is very crucial so that the drone doesn't crash into a building or a person. And also finally comes faults, which is going to be the main focus of this topic. Recently, I came across a video where a drone was tested for some package delivery. I'm not quite sure of the company, but when they were trying to test it out, deliver an actual package to an actual person, it went and crashed onto the person. That tells that there is some problem for the industry due to faults and malfunctions that happens in drones that can cause severe damages or even deaths. So UAV control in general is a problem, and faults in particular is something that is of interest to many people in this era. Now, this is a block diagram of a flight control, which is like the main methodology of my research area. It has four main parts, and part one is on developing a mathematical model that is fairly accurate and that has all the uncertainties that is required to design our control algorithm. Part two is on the development of this control algorithm and how we can make this control algorithm robust to faults and various other uncertainties and maintain a stable flight even when uncertainties such as faults, motor faults, or anything that happens. And a third part is basically to evaluate how well this control algorithm performs via a computer simulation. And the fourth part of my research is, okay, we designed something that works very well via computer simulation. How well will this same algorithm perform when we deploy it to an actual quadcopter and when we fly it? So I'll be talking about these four parts of my work in this presentation. So first, let's look into the mathematical model. I'll keep it a bit high level. I wouldn't go very technical. So the first thing is when we design a mathematical model for the quadcopter, we come up with a set of assumptions. Some of the assumptions are that the quadcopter is considered to be a rigid body, which means there is no motion with respect to the body frame. For instance, flexible bending and movement of the components on board are considered negligible. The quadcopter is also assumed to be symmetrical with constant mass, and also there are various different configuration of a quadcopter. It can be considered as a plus or it can be considered as a cross. But for my research, I've selected a X-configured quadcopter in physical layout because the industries and various different quadcopter platforms, they use this X configuration for their physical layout. Then the quadcopter can move and rotate in 3D space, and the motions are generally movement along the N, E, and D axes. N, E, and D refers simply to the north, east, and down axes. We don't consider up for the model due to certain reasons, which I wouldn't go very detailed. But the drone can move along N, E, and D axis. Then it can roll along the X axis, it can pitch along the Y axis, and it can yaw along the Z axis, which means it can move along 6 degrees of freedom. And it has 12 state variables, which are linear positions. We call it NED, which is the altitude, the lateral and the longitudinal position. Then we have the roll, pitch, and yaw angle. Then we have the linear velocity, which is represented as U, V, and W. And we have the angular velocity, which is represented as P, Q, R. And these variables are related to each other by a set of equations which describes how their motion changes over time. We'll look into this a bit more, and then we'll get into the second part, which is the control. Now, the inertial frame, that is the ground, and the body frame, that is the quadcopter, are shown in the figure. The equations of motion that describe the changes in the position and attitude of the quadcopter are with respect to the inertial frame. However, we all know that the forces and moments are expressed within the body frame because the sensors and the propellers are attached to the drone. Therefore, we need some sort of a mapping. We used Euler angle approach to model the rotation matrix R and the transfer matrix T to transform between the body frame and the inertial frame. And these two equations are shown in the screen. Once that's done, we move on to kinematics, which refers to the position, velocity, and acceleration of the drone. It relates the motion between the inertial frame and the body frame using the coordinate system. The translational kinematics with respect to the inertial frame is related using this equation where linear velocity is in the inertial frame is equal to the rotation matrix multiplied by the linear velocity in the body frame. And similarly, the rotational kinematics with respect to the inertial frame is related using this equation, where the derivative of the attitude in the inertial frame is equal to the transfer matrix multiplied by the angular velocity in the body frame. So once we derive these kinematics, we look into the dynamics of the drone. So dynamics refers to the forces and the moments of the drone. And to derive this, we use the Newton-Euler formalism. The translational dynamics, that is the forces acting on the drone, is expressed using the well-known force equation F equal ma. And the omega cross mv here refers to the centrifugal force. Similarly, the rotational dynamics, that is the moments acting on the drone, is expressed using moments equal moments of inertia times the angular acceleration. And the omega cross I omega refers to the centripetal force here. That's quite a bit of mathematics there. In summary, what we derive the dynamics of the quadcopter in the body frame because the sensors are attached to the drone, and we use the coordinate system to derive the kinematics in the inertial frame. And then finally, we also derive a simplified model, especially a simplified model of the full nonlinear quadcopter is for tuning and designing purposes. So we used a simplified model to tune our algorithms and develop algorithms, but we test these algorithms on the full nonlinear model of the drone. Apart from the quadcopter, the drone model itself, there is a bit of propeller dynamics. It is also derived as the thrust and torque are generated by the propeller, and it directly affects the motion of the drone. The quadcopter is controlled by adjusting the control inputs, which alter the speed of each motor through something called the motor mixing algorithm. And for each quadcopter propeller, there is a force generated and also a torque about the center of gravity of the vehicle. And the coefficient KT and the coefficient KB you all see on the screen is the thrust coefficient and the drag factor of on the propeller respectively. So that's all about the mathematical model. I wouldn't want to speak more about the mathematics. So in terms of the control, I'll talk a simple PID flight control architecture. So there is a position controller, which is the outer loop. What the position controller does is it is required to maintain the altitude of the quadcopter with respect to the reference altitude. And also it tracks the longitudinal and lateral position and provides the reference values for the roll and pitch angle with respect to the reference longitudinal and the lateral position. Then we have the attitude controller, which usually works at a higher frequency and generates the rolling, pitching, and yawing torques to stabilize the attitude of the quadcopter. Then we have the planner, which generates the trajectory. It consists of the reference altitude, position, and the yaw angles. We have the output from the controller, which is the desired thrust, roll, pitch, and yaw, which get mapped to individual rotor speeds through the motor mixing algorithm. The controller works for the fully nonlinear quadcopter UAV model, which we discussed previously. And the feedback from the model is used by the controller. And there is 6 individual PID controllers, which all work together to stabilize the drone. Then we used something called an RLS for fault estimation, because to compensate for faults, we need to first be able to know what the fault is. And RLS is an algorithm used for estimating the parameters of a system. It's based on least squares, which minimizes the sum of squared differences between the output observation and the corresponding information matrix. Now here, it uses the input to the model and output from the model to estimate the actuator faults. So the RLS equation is y equal x theta. Y is the output observation, x is the information matrix, and theta is the parameters to be estimated. And in our case, theta is the faults that we want to estimate. The full equations are as follows. It uses the full nonlinear model. And finally, once these are estimated, the estimated motor fault is used by the flight controller using a simple scaling law to compensate for the faults. Let's get to the more interesting parts. Now the mathematics are over, the control algorithms, the equations are over, and now what we developed in action, how it works in simulation and practical flight test. So the picture here is a Simulink model we built. It has the mathematical model of the drone. The dynamical response of this mathematical model was first tested before we bring it to the simulation. And then it has the control algorithm, which we developed. It has the planner, which generates the reference values for the control. We have the noise and measurements added to our measurements. And then we have scopes and visualization to see what's happening in various parts of the simulation. The model parameters used for the simulation and the respective values are shown here. This is from a drone we have back in our center, and we got these values based on some approximations. And first three main experiments were done with the simulation. We checked how the controller works in a normal situation and what happens when a fault occurs and how our controller reacts to faults. So I'll show some simple animation here. So we tested out our PID controller, and the reference values for this were provided by the motion planner. A simple trajectory with 0 yaw was considered to validate the tracking performance. So the results were good as expected in the simulation. The controller was working fine. The model was representing an actual close enough quadcopter, and we were able to see fairly good enough results. So that's you're seeing a drone following a trajectory. I won't wait till the entire simulation runs, but let's go further. Then we wanted to test out how does the same algorithm performs when a actuator fault happens. So actuator refers to a motor. So when one motor reduces in efficiency, maybe a coil burnt, something happened to a specific motor, how does the drone react? So first, we considered one motor fault, and we just degraded its performance by 10%. So it was tested out with 0.9. It's represented as 0.9, which means there's a 10% loss in efficiency. And the drone, there was offset, but the drone was able to still maintain some trajectory. It didn't crash. When we increased that 0.9 to 0.6, which means a 40% reduction in the efficiency of the motor, maybe 2 or more of its coil has burnt out, let's assume. In that case, the drone simply crashed. And we took this further, of course, to a 4 motor faults where every single motor experiences different efficiency drops. And we wanted to see how that happens, and as expected, it simply crashed. Then for the same severe motor faults condition we saw earlier where the drone just crashed, we wanted to try out how our adaptive control worked, and our proposed algorithm, though even during this severe motor faults condition, it was able to still maintain trajectory. The results were very impressive, and as it can be seen from this figure, that the motor faults of each motor was accurately estimated within 0.04 seconds, and various other faulty conditions were also tested, and in all those situations, the drone was able to maintain trajectory. Now, if you all have done practical work, many you all will agree with me. How it works in simulation is not how it works in practice. In simulation, everything is perfect. It's a simulated world. It most of the time it works in your favor. However, when you put that if you put the same algorithm in the actual drone and go out fly, you don't see the same results. So we took our algorithm to the next step. That is, we wanted to test it out practically. And for that, this is my methodology. So the first stage is the plan mission stage. The flight path for the mission is generated using a commercial software called Q-Ground Control. It's an open source ground control station software used for real flight and also being used commercially a lot. Now the waypoints generated from this trajectory is used in the design and simulate stage, where the custom flight control algorithm that we tested via the computer simulation is implemented. This stage defines the quadcopter model as well, runs something called a scenario simulation with tools like Unreal Engine. Scenario simulation is optional, but it adds a realistic flight environment visual to observe the performance. And finally, in the validate and deploy stage, the model we generated, the model we created, the controller we created with in MATLAB and Simulink, we used something called C code embedded code generator, and we generated the C code from the design model. And this generated code, which is a C++ flight code, is used for software in the loop, hardware in the loop, and is ultimately deployed into the actual flight hardware using a support package offered by MathWorks, which is called the UAV Toolbox support package for PX4 autopilots. We were able to do software in the loop, hardware in the loop. These are different workflows, but for this presentation, I'll focus only on the hardware in the loop. And the hardware is shown here. It consists of the Pixel, GPS, motors, batteries, and so on. Before taking the drone out there and flying, it is very important for us to do some bench test. That is, connect the drone with the laptop, use the toolbox, and test various different cases. We carried out so many bench tests and see if the quadcopter responds, if the sensors are working fine, if everything else is working fine. We also did various other experiments to make sure that when we designed the controller, it was the dynamics relates to the actual drone. So we needed to find the motor characteristics like the thrust and the torque coefficients. So we used a thrust stand which was available at our uni. We connected one of the drone motors and we were able to collect data, plot data, and see the coefficients and take these coefficients to our controller designed so that when we fly out, the drone doesn't crash because of poor design. We also did some experiments to determine the mass properties of the quadcopter. This is where we hung the drone and we oscillated it and we measured the period to calculate its inertia in all three axes. And we were able to successfully do our hardware in the loop testing. So this is where the drone is connected to the laptop. On the left side of the screen, you'll see the Q ground control, which plans the mission. It's the same software that is used commercially to plan mission flights. Then the mission is planned and the mission is sent to the drone. And on the right side of the screen, you all can see the drone dynamics working in real time. And also the generated code from our controller design was implemented straight in the flight into our drone hardware, and which was connected to the laptop, and you all can see everything running in simulation. So this is something called a hardware in the loop testing, where the hardware, the drone, is connected to the laptop and you all are able to see how it performs. I wouldn't be, I guess 2-3 minutes are left, so I wouldn't be waiting till the entire video, but I'll be going to my next slide. So once we were happy with the performance, how the drone performed in hardware in the loop, the next obvious step for us is to fly it. So we included many safety features like kill switch, geo fencing, ceiling clocks, termination, and we successfully carried out our flight. We went outdoors, we flew, and there's a video showing how the drone flew. Now we did various different tests, normal, like a test in the normal situation with waterfalls, and we were able to get various different results. I promised myself I wouldn't be discussing too many results in this presentation, instead try to keep it very top level so that we have a wider audiences so that everyone will be able to see what was done in our research. So I again wouldn't wait till the entire video. Let me go to my last slide. So I'll talk a bit of limitations, recommendations, and the impact our work created. So the outdoor flight we did, it wasn't a controlled environment. It was uncontrolled. We didn't have control over winds. There were some GPS inaccuracies because these are quite normal in practical settings. And what we can do is if we suitably have an indoor flight testing environment, that's awesome. We also need to follow CA regulations when we do our testing, and UK has strict operational safety regulations. And also the flight controller board we used, it lacked some amount of CPU and memory resources, so we couldn't test out advanced versions of our algorithm. Some recommendations are like along with the uh, flight hardware, if we can use a companion computer like the NVIDIA Justin or a Raspberry Pi to complement the flight controller and to basically transfer the estimate algorithm to the onboard computer to offload the computation within the flight hardware. That's a good recommendation. However, the communication between the onboard computer and the flight hardware needs to sync very well. Also, if you can use optimization to fine-tune controller filter coefficient to minimize tracking errors, that's another recommendation. Some of the impact is it reduces the risks of unexpected drone crashes, protects the public, and supports the UK's plan for safe integration of drones into the future transport and logistics network. And extensive high-fidelity simulation, hardware-in-the-loop experiments, and real-world flight tests. These are very comprehensive, and it ensured both theoretical rigor and practical feasibility. And with that, I would like to thank you all, and I'm open for any questions or suggestions.
Okay, thank you, Ahsan, for the presentation. We have 3 minutes. If someone has a question, any question from the audience?
I guess drones are very boring for them.
So I will have some questions about the math part, but I will not ask it here. I will ask it later from you. Anyone else with any question? No? A general question, not a math question. So you played with the coefficient. There was one slide that if one of the what do you call it, these rotor motors or is not, so the coefficient 1 to 0 was the, if it is working fully correct, or 0 is not working at all, and the number between is like with some fault, right? So if you make one of them 0, can the other 3 somehow you manage it to keep the balance, or no, it's too difficult?
That's a very interesting question. Let's imagine a drone flying from, let's say, UK to Iran, and middle of its journey, let's say one motor, as you are saying, completely failed, meaning it stopped working. So now a quadcopter has only 3 motors. So the finding from my research, yes, we were able to control the drone, and I will give a bit more technical answer. So what, from a control perspective, happens is the quadcopter, the estimator, it estimates, oh, one motor is completely gone, and it informs the controller, hey, now one motor is gone. You are a quadcopter by the physical layout, but I want the control algorithm to react as if it's a very unstable trirotor. Try to control it from that perspective. So the drone identifies that a motor has gone bad, and the controller tries to tackle that, thinking the drone is a very unstable trirotor, and it still tried and manages to control. However, there is some losses in the performance. The yaw stability is gone. We cannot regain yaw stability. However, the simulation, we saw that the drone was able to stabilize and just land safely without crashing.
So one comment from Treso, and then I will go for the closing notes of the session, a few announcements. So Treso is saying, I'm very surprised by everything you did. A short question, how much would everything change if the assumptions are modified? For example, a bird crash might increase the weight.
Yes, now birds or anything in the air is a big threat to all UAV operators. So if a bird, depending on the crash, the drone might, if the bird gets stuck into the drone, it usually it might be a disaster. However, when I had the same question during the second year of my PhD, how can be like bird crashes and birds or things in the air. How can this be tackled? One thing we all agreed is that these drones, they make a lot of noise. So birds, they get afraid unless it's a very, very brave bird. They usually go away. They don't come closer to the drone. However, your question is valid, Tere. So let's say something else, like a bird dropped something on the drone, or some other crashes, a drone crashed with another drone, or something got tackled. Then the situation can get tricky, and the obvious answer is that the drone would crash. And our work doesn't look very deeply into situations where anything that can come in contact while the drone is flying.
Okay, thank you for the presentation and also the answering the question.